So let's take a look quickly at the history of how our universe came to be as a template for looking at evolutionary biology. All matter in the universe was all compressed into one small point, and that small point exploded with a force that we cannot imagine. And that explosion we call the Big Bang. Now it's possible that we had multiple Big Bangs, but the most recent Big Bang that generated the universe that we're part of started at about 13.8 billion years ago. So approximately 13.8 billion years is the jumpstart for the modern day universe as we know it. Now, if that Big Bang theory is correct, and it is being modified and thoroughly studied by many people right now, so our hypothesis of how the Big Bang operates is constantly in flux. But if that did take place, then the universe consisted of a chaotic swirling cloud of hydrogen and helium, these very essential elements that we call a nebula. Then as the hydrogen and helium nebula was spinning, it was full of a huge amount of heat. It went through an ongoing process of rotation and heat loss. And as it rotated, the rotating mass of gas and essential elements were transformed into a spinning disk. And in the middle of that spinning disk, there was a center bulbous area that we call a nebula. And that bulbous nebula continued to collapse inward on itself, drawing in matter from the rest of this immense distribution of gas and elements. Well, in the middle of that nebula, eventually there became a condensed, very tightly woven ball, if you will, of hydrogen atoms that were colliding and fusing together to create more elements. So we started off with just the basic element, helium, and hydrogen, and then helium. And then we moved to a condition where those elements were being compressed on themselves and fusing. And that nuclear fusion then is what generated all the rest of the elements that we know of in our solar system. So that initial nebula then kept compressing and generating through nuclear fusion all these elements, and then it formed a sun. So this is the general concept of how then that sun is a body of very condensed gases and elements, and it radiates heat and light. And then the solar system then forms around that as the sun nebula center continues to evolve. So this is kind of the basic template then to end up with a central star that has a lot of material, elemental material that's spinning around it that can then evolve to the next step of actually having a star with planets around it. So one of the most famous and important examples of this is what we call the Eagle Nebula. And the Eagle Nebula was photographed by the Hubble telescope, illustrating the synthesis of stars through this nebula spinning disk rotational process. So once we got a structure of a star going through nuclear fusion and then having all this material swirling around it, that material continued to cool, and it also collided with each other. And as you had very small elements and start to fuse and come together, then they would stick together and form larger and larger masses of rock material. So in this cooling, spinning process that's around the stars, then that material would accrete together and merge to form what we call planetismals. Planetismals are these proto-early types of coagulated groupings of matter that are eventually then going to be turning into planets themselves. Well, the planetismals continue to collide. They merge over and over again through this rotational process, and then we end up with a true planet. Now, the outer planets, in addition to having this kind of dense rocky core that was from this accretion in the spinning around the star, the outer planets also accumulated very huge amounts of gas. So that's why we have this structure of the inner four planets are rocky, the outer four planets are gaseous giants with a rocky core in them. So in this process then we finally establish a sun with a rotating series of planets around them. And then we have a lot of material that has not been accreted together to actually form a planetismal or form a planet. Then at that point, then the solar system and Earth itself began to take on a structure that is not that dissimilar from what we see in the modern day. So this This model of a stepwise progression from individual materials that group together then to form larger materials called planets, that puts into place then the idea of the structure of the inner and the outer planets. Now at that same time, planet Earth itself was going through a very strong series of changes. And when you first accrete together these individual fragments of ash and dust and smaller particles that group together, they begin to heat and they become compressed. And when they do that, then that process drives what we've called the differentiation or the structural genesis of the Earth. The modern day Earth has a solid and brittle crust that's on the outside. Then we have a very large component within the Earth that's composed of molten rock. We call it the mantle. And then within the core of the Earth, we have a solid core and a liquid core. So the Earth structure of having a crust, a mantle, and a core, that was all established in this early time period as well. So this idea of accreting smaller particles into larger particles, having those large particles form planets, and then having that material become dense and hot. When you get the large accretions of these into a planet-sized object, one of the results is that you have chemical transformations, but also physical transformations that make the center of the planet hot. And then the heat is being dispersed outward from that. Now, one of the next questions is, well, how do you make things round? And the roundness of these accreted planetary bodies is caused by their spinning rotations that go through the solar system. So not only just the motion through the solar system, but actually the spin of the planet itself. And in the end, this makes a spherical body. Now, the Earth is not perfectly spherical. No planet is perfectly spherical. But for most practical purposes, looking at it as a sphere is a pretty useful model. It's actually ellipsoidal in shape because of the stresses that are put onto the planet as it's rotating and spinning.